So here we're going to wrap up the last couple of items related to graphing. So this will be, I'm going to make a list of everything that might be done with a function. Not all of them are asked all the time. Keep that in mind, and you'll see the last homework that I posted today or for Friday. It's very specific about what it asks you to do, so take note of that. That'll be the way it is on the test. So one thing that we've looked at, we have domain, which more reality is more importantly the holes in the domain, the discontinuities. Okay, so then what we're going to add, one of these, this is an addition for today. Discontinuity analysis. Okay, the good news is we already know how to do this. It's a problem that we've already done. We just didn't relate it to this. Okay. And then also new end behavior. And the order, you know, doesn't have to necessarily go in this order. And what this relates to is what we call horizontal asymptotes. And then things that we've been doing, you could pretty much count on this with everything. Increasing and decreasing behavior. What intervals? And we locate local max and min. And for some functions, particularly polynomials, we might ask for intervals of concave and up and down concavity. And with that, of course, inflection points, changes in concavity. Okay, so again, any of these could be asked for with any type of function. So what I want to do here is address these two items. So discontinuity analysis. So again, think about the process. You look for the domain, find the domain, it's got gaps. Those are the discontinuities. We want to know what's happening there. Analysis. So, of course, you cannot find out what's happening at the discontinuity because nothing's happening at the discontinuity. The discontinuity is a place where the function's undefined. But what we can find out is what's happening near the discontinuity. How do we do that? For any and all discontinuities, discontinuity. And we'll just give it a fake number, A. So say you have discontinuities at 2 and 3. You will do this for x equal 2 and x equal 3. This is an old problem. We evaluate the limit as x approaches A, and this tells us of the behavior near the discontinuity. So we go back to month number 1, and you direct substitute A, and the easy ones, obviously, you get a real number and you're done. In this case, that'll never happen because A is a discontinuity, so A won't work in the function. So the other two choices we had when you direct substitute is you got non-zero over 0, and you got 0 over 0. So in this case, we knew this was an infinite limit. we evaluate right and left hand sides. And I'll just pick a number as an example. So let's say, whoop, that's 2, just to give an example. So I find out this is a discontinuity, and what I would do is evaluate this limit. This would be on the right, and let's just, this is just an example. I don't even know what the function is. On the right of 2, I'm going to positive infinity. So what that looks like graphically is this. Now what it does down here, I have no idea. But as I approach this line of 2, it's going to go to positive infinity. It could also go to negative infinity, in which case I draw it down here. So what I'll write as I approach 2 from the left, let's say that that one does go to negative infinity. And sorry about that. And that would look like that. And you get the point. So they could both be up here, both down here, this way, this way. But the key is you have a discontinuity, again, to repeat. You have a discontinuity, you direct substitute, non-zero over 0, and that led to this. So we did these types of problems on exam 1 and 2. Now the other case was 0 over 0, and usually those involved a factoring. So you would factor and then you would cancel. So this is a terminology. This discontinuity is a vertical asymptote. Okay, it's a construction line more or less. It's not part of the function. The dark line is the function. We draw it as a dotted line and we label it. We want to label everything. Label, label, label. That's the equation of a vertical line. Okay, so this is a different type of discontinuity. So you remember, we get 0 over 0, we factor, and let's just say, we use 2 again. Limit as x approaches 2, and let's just say it equals 4. Well, what does that mean? That means as you approach 2, you're approaching 4 up here. But we're undefined at 4. That's why we're doing all this. So this is what you call removable. It's one of those open circles that we had when we played around with the graphs of this stuff. This is called a remove. It's a hole. It's a gap. It's an open circle. It's a removed point, essentially. Removable discontinuity. So we'll do this. If we have discontinuities, we'll do this so we know what they look like. Just a quick example, and this would be, again, part of a bigger problem with more of the things on that list. But let's just do this for it. Real simple example. Okay, super simple example. Okay, discontinuities. So clearly the bottom can't be 0. So we have one here at 4. So if I'm thinking about this graphically now, if that's 4, I won't label it yet, but something's happening here. I want to know what. How do I find out what? We'll let x approach 4. And I get 1 over 0. I get non-zero over 0. So immediately I know, and I kind of missed that. That's right. I know I got an asymptote. And I know I got to check the right and the left. So these numerators are positive. 4 right, positive. 4 left, negative. So I know the behavior. So if I'm building this as I go through the steps on the items on the list, I come over here and I say, okay, I figured this is an asymptote. On the right, I'm going to positive infinity. On the left, I'm going to negative infinity. And then you add the other pieces. Okay? So end behavior, what is that? And I talked about this in another group. So there are some notes already created. So I'm going to put this down like a slide almost. And I would advise, if you want, pause it, write this down. Okay, what's end behavior? End behavior answers the question of what's happening to y as x goes to infinity and negative infinity. And what that means is what's happening in this direction as we go way out to the right or way out to the left, however you want to describe that. Now we know end is misleading, it doesn't end here. But the way we write this would be an example as x goes in either direction, y is going to infinity. So this would just keep going, right? Like our old friend, the parabola. Kind of boring. And this is the same, but going the other way, right? As we go far to the right, far to the left, the function's going to negative infinity. Again, sort of boring. So the more interesting case is in either direction, and it only really has to be one direction, but it's typically both the same idea. You approach a value, L. And in this graphical example, this is L, whatever it is, y equals 2. So we're going to approach out here. So this is describing what's happening away from the origin. In this vertical line, we're going to call a horizontal asymptote. And we approach here, we approach here. So the big question is, how do we find them? And we have a nice little shortcut. Oh, another sheet. Again, another previously created sheet. So why don't I give you, I'd advise you to pause again, write all this down. Okay, so the line y equal L, which is a horizontal line, is called a horizontal asymptote if one of you're getting this behavior. As x gets large, you're approaching a value, or x gets large negative, approaching a value. And like I said, typically it's the same on each end. And we call that a horizontal asymptote. So there's a semi-formal definition. So this is how to do it. And really what this is saying is how to find horizontal asymptotes. And there's a definition to start this off, and it's called degree. This is degree of a polynomial. That is the value of the largest power or exponent. And what we will do is we will compare, put that there. Let's make that a cube. 3x cubed plus 1 over x squared. We're going to compare degree of the top and bottom, the numerator and the denominator. So if I have, in this case, the numerator is 3, degree 3, this is degree 2. The numerator exceeds the denominator, you have none. There are no asymptotes, so you have essentially something more like this or this. So if that's the case, you don't worry about them. So I flip them. Now the 2's on top, 3's on the bottom, so the degree denominator exceeds the degree of the numerator, and that indicates that you have an asymptote at the x-axis. So you'll see things that, you know, look like this, right? That's the x-axis. And now we don't put a dotted line up over top of a solid line, but we label it. Okay, that's the second case. And then the more interesting case you can see is when they're equal. So these are both of degree 2. And you see this, what this says is ratio of leading coefficients is a horizontal asymptote. What the leading coefficients are, they're the ones attached to the highest power. So this leading coefficient is 3. This one is understood to be 1. And their ratio then is 3 to 1 is 3. So for this specific case, if I'm building as I go, maybe I already have some other information, but once I get this information, I put a dotted line at 3. And then when I go back to complete the graph, I know I gotta be here, and I gotta be here. So maybe it does this. I don't know, maybe it does this. Maybe it does, you know, this. Or something in between. But I just know at the ends, I gotta be here at 3. So what I would plan to do is walk through a couple of problems in complete fashion on Monday. So this is an important homework assignment. So see you Monday.